Let's begin with a simple question. Why does copper allow electric current to flow easily while rubber blocks it completely? The answer lies in a property called resistivity, denoted by the Greek letter ρ. Resistivity tells us how strongly a material opposes the flow of electric current. Unlike resistance, which depends on the length and area of the wire, resistivity depends only on the nature of the material. The formula is ρ equals R multiplied by or divided by L, where R is the resistance, A is the cross-sectional area, and L is the length of the conductor. Its unit is ohm meter. As shown in the diagram, resistivity helps relate resistance with a material's geometry. Now let's classify materials based on their resistivity. Conductors have very low resistivity, around 10 to the power minus 8 ohm meter. Semiconductors have intermediate resistivity, which depends on temperature. Insulators have very high resistivity, often more than 10 to the power 13 ohm meter. For example, copper and silver are excellent conductors. Silicon and germanium are semiconductors. Rubber, wood, and plastic are insulators. On the bar graph, you'll see how resistivity varies drastically across these material classes. Semiconductors behave differently from metals. As their temperature increases, their resistivity decreases, the opposite of what happens in metals. This happens because higher temperature provides energy to break bonds, releasing more charge carriers. The resistivity temperature graph slopes downward for semiconductors. For example, silicon and germanium show this behavior clearly. Also, by doping, that is, by adding impurities, we can lower their resistivity further. That's why semiconductors are the foundation of modern electronics. Alloys like nichrome, manganese, and constantan are used when we need materials with nearly constant resistivity. Unlike metals or semiconductors, their resistivity is almost independent of temperature. This makes them ideal for heating elements in electric toasters and iron's precision resistors in electronic circuits. For example, nichrome is used in electric heaters because its resistivity remains stable even when it gets hot. As shown in the flat curve diagram, resistivity stays nearly constant for these alloys. Here are some real-world examples of resistivity. Copper, 1.7 into 10 to the power minus 8 ohm meter. Nichrome, 1.1 into 10 to the power minus 6 ohm meter. Silicon, 2.3 into 10 to the power 3 ohm meter. Rubber, greater than 10 to the power 13 ohm meter. That's a range of over 21 orders of magnitude, showing how diverse materials are in their ability to conduct electricity. To wrap up, let's revisit what we've learned. Resistivity, denoted by ρ, tells us how strongly a material resists current. The formula is ρ equals R multiplied by or divided by L. Conductors have low resistivity. Semiconductors have intermediate resistivity that decreases with temperature. Insulators have very high resistivity. Alloys are used when stable resistivity is required, especially in heating and measuring devices. So, next time you plug in a device or flip a switch, remember, the material choice was guided by its resistivity. In our next lesson, we'll explore how temperature affects resistivity quantitatively and how we measure this change using the temperature coefficient of resistivity.